like to eat more than they do now, but we'll see how that goes. And traps will be feed crops, and that has a pretty high impact, but it's not as high as feeding all those people. If we can feed them with calories from plants, it would be a lot more efficient than feeding them calories to feed, but right now we think we can do feed, and we can do it with Lotus japonicus because Lotus has all the traits and all the stuff in play, that you can do molecular genetic studies pretty quickly. I'll skip this last track. Okay, so here's a top candidate. I just wanted to tell you why I think this is possible to even get people to eat something like chickpea more, right? So it's a protein-rich crop. It returns nitrogen to the soil. That's all good. It's a major source of feed for animals. All these legumes are. Chickpea also is for animals. And well adapted to semi-arid climate. So right now, farmers really like to grow it because wheat is losing a lot of money for them. So wheat loses $21 per acre in North Dakota, while chickpea is giving the farmer $140 per acre. So farmers are businessmen, so guess what they're doing? They're not growing wheat, they're growing chickpea. And so right now, in the U.S. refrigerators, apparently, 25% of them have hummus in it. So I think this is like the 70s hippie culture coming back. And so here we go. Maybe people will start eating chickpea. And chickpea has perennial varieties, and its genomes of many of them have been sequenced, and so we should be able to have directed breeding that will help us get this idea out. Okay, so our 10-year vision as a team is shown here. These are some of the milestones we have and how much money we think it will cost. So we're thinking for $50 million, we can get rid of half of that extra CO2 up there within 10 years and contribute to the world's food supply sustainably. So I think it's a pretty cool vision, and we're really excited about trying to get this all to work. And here's, I think, the team. So here's our team with me. I'm the head of the team. And we have Jonah Well, who studied the evolution of biochemical pathways and secondary metabolism of plants, so he'll be our super expert. Wolfgang Wiss is our root expert who we hired just recently. He has genes that he knows he can mutate that will change the root architecture from being one that spreads to one that grows deep. So he can find those mutants, and I think we'll be able to find them in the crops that we're interested in. So that'll be cool too. And then we have Joe Edler, genome and epigenome expert, as well as Jubilee, who does epigenomics. Okay, I wanted to leave you with this last thought from Jonas Salk. He already came up with. Our greatest responsibility is to be good ancestors, and I think that's the reason that we're really motivated to do this. Because we inherited the planet. Anybody who's my age inherited the planet with a lot less people, and we took advantage of it. So now we're living it for our kids in a mess. And so I don't want to leave it that way. So Scott is motivating all this stuff. And that's the end of my talk. I want to thank you for coming. Wonderful. Okay, you have a question right here. If you stand up, you get the microphone. Squeezing through. Your discussion is super fascinating, so I started Googling right away, and I guess it's completely hydrophobic. I'm wondering if it can also be used as a way to capture water in the soil to counteract drought? Yeah, I think it is used that way. I mean, that's what people think it mostly is doing for a plant. Is that it actually is both flooding, it makes the plant both flooding and drought resistant. So, I mean, I think it's a good barrier in that sense. And a lot of the coastal grasses make quite a lot of sugar in it because I think that's what they're doing. They're keeping all the water out of certain types of plant. Here's the right plant.
Hi, thanks. That's a really interesting idea about modifying the plants. And one political and social concern I have about actually achieving this and getting buy-in is that so many of the people who are concerned about global warming are also, a lot of them are also very concerned about GMOs, and I think that's something we need to overcome. And I'm wondering if you can talk about that, because this is obviously a GMO issue.
Well, I don't think it is actually obviously a GMO issue. We've thought about how to do it without involving a GMO at all. And so we can do it by breeding. I'm pretty sure that that'll work. And so that's what we have to do. We'll do it. I think if we did it with GMOs, we would do it faster, but it's just how people feel. I really want to get into the GMO debate. Let's just put it that way. So, yeah.
So Joanne, that was really energizing. I have to say that you're a breakthrough prize winner. If you get that vision accomplished in 10 years, you'll be guaranteed to be the first double breakthrough prize winner.
I'd like to ask, do you foresee a period of breeding, constantly growing and selecting populations of these plants in order to optimize their capabilities? And would that be speeded by indoor growth techniques, some of the new techniques that allow you to cycle all year long very rapidly?
Yeah, so a big part of what we've raised money for already, we've raised about $7 million total, is for what we call climate rooms. And so these climate rooms, I mean, it's not exactly what you're talking about, I don't think, but we have collaborators already in place who might be able to grow a lot of these seeds for us. But the climate rooms are going to tell us where, what's going to be the best environment for a certain variety. And so we can simulate almost any climate on the planet right now. And except for the really cold ones, that's a little too expensive for even our climate rooms. And so we're doing that, and that's going to be one of the methods that we get plants to make more sugar in, I think, is like where they're growing is probably going to have an impact on that. So that's a big part of what we'll do.
Great.
Joanne, can you speculate why microorganisms have figured out a way of using sugaring as a delicious food?
Well, maybe there's not that much exposure, to it, really, because, it's inside the plant. It's outside of the cell, but it's inside the plant, So maybe there's not a lot of microbes that have penetrated to get in there. But it's polyester, and I think they use probably, that's the part that looks like the most stable part of the molecule. And so I don't really know enough about why they're on that, because the soil is so rich in all these activities of microbes, And so you would think that maybe there's somebody out there that can get in and figure out how to break it down. But so far, the most stable carbon compounds in soil, if you go take soil samples, look like major carbon superman. And so there was a plant there probably that died, but the superman's still there. It's really stable. Yeah.
Okay. Just quick follow-up on the
one of the nicest things about your plan is that you're planning to use existing croplands. Do you have any concern that this will be so good that people will actually bring some of the remaining ecosystems into play with this crop, and that it will actually end up resulting in the loss of natural ecosystems?
It could happen, but I think what we're going to do, I think we're going to try to maximize these marginal places where there's a lot of grazing going on. Those ecosystems are already lost as far as I'm concerned. Yeah, we're not going to try to go into the best places, or wreck some place that's a really good ecosystem in terms of its interaction with the world, the carbon cycle and all that. Yeah, I don't think that would be a problem. I could be wrong. Yeah. Well, we haven't really brought about climate side extreme, I don't think, at this point. But yeah, maybe it could happen, I guess. Wonderful. Actually, thanks to all you guys for a wonderful time.
Okay, of course, it's an absolute honor and a pleasure to be here, to be able to talk with you. And so I want to focus on this, I want to talk about the future, one of the future avenues in our field, and that is measuring gravitational waves from the birth of the universe. And in 10 years. And the exclamation point is because it's really, really cool, and it's fun to do, and if we do it, it'll be huge. And the question mark is, we don't know if they exist at measurable levels. Okay, so this is what we're going after. Okay, so what's this picture? This background map is a map of the sky, of the temperature fluctuations in the sky, and you can think of this, that's flat. Here's a round version, and with the galaxy in it, the galaxy's been removed from that. From the reddest red to the bluest blue there is about 400 millionths of a degree centigrade. So those are the fluctuation levels that we measure. And when we think about that, when we just look at that, you can think of it as a heat map of the universe that tells us about the strength of gravity over the universe. And we think about that model pattern as an impression of quantum fluctuations right from the birth of the universe. So that is quantum mechanics writ large across the sky, say by this process called inflation. Okay, so what is a gravitational wave? If you were here last year, I'm sure you heard a lot about them, and it's this propagation at the speed of light through space-time. And I'm just going to limit, when we talk about it, we'll just limit ourselves to the spatial part. So what happens? So that those arrows are supposed to give you the picture that the gravitational wave is propagating that way. It squeezes space this way, expands it this way, and a half a cycle later, it squeezes it this way, and expands it this way, and then it goes on like that. And so how do we quantify that? The way we quantify that, and this is our prop number one, is with a strain. So what is a strain? It's not psychology or anything like that. A strain is, and this is roughly a meter stick. A strain would be in the squeezing of space this way. If we squeeze this meter stick by 1 centimeter, right, that would be 1%. And we'd say the strain is 1%. It's the change in length over length. Okay? So keep that in mind. So it squeezes it this way and expands it this way, and 1 centimeter is a strain of 1%, 4.01. And the way we quantify that is we use H. So what LIGO discovered last year, or 2 years ago, was 2 inspiraling black holes. Okay? Those inspiraling black holes produce gravitational waves, and the strain that they produced was 0.20 zeros and a 1, 10 to the minus 21. Okay? And that corresponds to a difference of about 1 human hair between us and the nearest star system, Alpha Centauri. Tiny. I mean, it's a testament to how incredible LIGO is as an instrument. And the waves that led to that oscillated, that oscillation that I tried to give you an image of, was about 100 times a second. Okay. So what are we after? We are after gravitational waves produced from the extraordinary densities at the birth of the universe. It goes backwards, much more compact and hot. Their strains could be as large as a part in 100,000. Right? Next to what LIGO measured, these are huge, right? They're enormous. The oscillation frequency, though, is very roughly, sort of 10 cycles in the age of the universe. Okay, so these are really, they're fixed on the sky. And if we detected them, and we'll detect them in the microwave, if we can, we'll see them in the microwave background, we'll get to that in a minute, they would provide us a connection between the quantum world, the same world that gave rise to all the fluctuations we see now, and gravitation. It should be amazing, certainly test for cosmology, and a link between, if you will, Einstein and Bohr that we have been searching for in physics for 100 years. Okay, so let me show you what it is that we actually look for. So this is a video made by a student who's now a sophomore, Raleigh Bova. And when it starts as a picture, it'll start out in our galaxy. Our galaxy is about 100 billion stars, and it's about 2/3 of the way out from it, 25,000 light years to the center of our galaxy. And then it's going to zoom out. Can you start the video and the music if it comes through? It's rocking right off. All right. And so see, you start off in the galaxy, and I want to give you a sense of the scales and distances that we measure. So there's I think it's centered on Stanford there. So. Okay, so those objects right there, these are some of the things we measured with our telescope. Those are groups of roughly 1,000 of our galaxies. Okay, so take 1,000 times 100 billion
and put them there, and that's what we see. And you can see how far away they are. Those are called clusters of galaxies. And there we go. You see, you start to get out, up near 1 billion light years, right? We're seeing out to 1 billion light years. The blue ones are from the Planck satellite. The red ones are from an experiment that we do. Actually, the LIGO source was about 1.2 billion light years away. And you see, we zoom out. Telescopes are like time machines. We look out. We look back. We keep looking out much further than those fixed objects we can see, and we look out to the cosmic microwave background. This sphere. Okay, here's my. So what are we looking for? What we're looking for, is, and you can see it's embedded in this black space, and we really think of it like that. These are gravitational waves that pervade space at scales larger than our observable universes, right? This is set by the age of the universe times the speed of light. And what these do, that same strain, if you will, these squeeze and expand the universe. The observable universe. And they're not all the whole size of the beach ball, but they can be, they can be like dimples in the beach ball, a fraction of it. Okay, so that's what and that's what we're looking for. And what they do, and the new signature, is they produce a characteristic pattern of polarization in this image. And so we're measuring the sky, not in temperatures you saw before, but we're measuring the sky with, if you will, polarized sunglasses for the microwave background. Right? So that means if you have polarized sunglasses and you looked at the sky, and you turn them, it would look different. Okay, you take your glasses off, you turn them, and it looks different. Okay, so we're looking for that, but we're doing it in microwaves. Okay, so how do we do it? Here's another. If you can click this video. So this is we have a set of telescopes. It's actually the group at Stanford, Charlie Kuo's group, is doing this at the South Pole. There's another set of telescopes in Chile. This is now led up by my colleague Suzanne Staggs at Princeton and Mark Devlin at Penn. And so this is at 17,000 feet in northern Chile. And we build these telescopes, and you'll see there's a community of them. And we have turned. You can see the far one there. Actually, Chuck Bennett and Toby Merritt are working on that one, and another group at Berkeley and San Diego are working on the one off to the left. And we're searching for this polarized signature in the sky. So, and very recently, Jim and Marilyn Simons have given us, we're very generous and given us funds to expand this whole effort and build a whole infrastructure up there. So in 10 years, when we found these and someone comes back and gives a talk, right, you'll see a much larger, you'll see a larger setup there. Okay, so how do we actually do this? What's involved? And what as I said, we're looking for this polarized signature. And when we did the WMAP, when we did that, we of course did it from a satellite, and we did it with roughly 40 detectors. And this gives you in advance 40 detectors at in round numbers, 100 degrees above absolute zero. We're now working with thousands of detectors. This is how much things have evolved since not too long ago. We're now working with thousands of detectors cooled to 100 millionths of a degree C above absolute zero. These massive arrays, and we're building up to look at the sky in 40,000 detectors all at once, and to search for this characteristic pattern. And I'm just showing you a few pictures there. On the bottom is a sort of typical detector system size, and just typical cryostats. This is what we build. It's a lot of fun, and there are a lot of groups around the world doing it. And so what is it then that we want to measure? Again, this is a simulation by Brian Keating and colleagues, and it has in a zoom in. So this is roughly 400 square degrees. As you can see, this is in the background there, in the red and the blue, are the temperature variations. And so their characteristic, if you will, scale of fluctuation is about 100 millionths of a degree C. The polarization, this one form of the polarization, we've already measured well, and measured well. We measured it with WMAP. We've measured it on the ground, and it's roughly a 20th of that in magnitude. So we're measuring that really well. We've even measured another form of the polarization that's roughly a factor of 10 smaller than that. So you can look at the numbers. This is now we're measuring characteristic temperatures on the sky measured in hundreds of nanokelvin, right, from an Earth that's in 300 Kelvin. So it gives you an idea of the challenges in doing these measurements. And we know, and actually it's Chaolin's group has the best limit on this. We know that this gravitational wave signature and polarization, which is a very particular characteristic signature, has to be less than something like 90 nanokelvin. So in the next, it should be, from just looking at all of our numbers, in the next decade, roughly, we should be pushing that down a factor of 10. Okay, so that's our goal. It's really exciting, and stay tuned. Good, thank you. That's great. All right, that's right there. Can you have the microphone really quick? It's being recorded in, so if we don't find it on the ground in the next decade, how much better can we do with a dedicated satellite? That's a politically charged question. I would argue that they're both really important. And a satellite, just to put this in two pieces. On the ground, we look at angular scales that are say, degree size, roughly. It's very hard to measure across the whole sky. A satellite, what's so beautiful about a satellite is you can measure the whole sky. And I would say if they aren't found on the ground or they're not hints, the motivation, the motivation is less. And it also depends on how well we can do. Right? If we run into some fundamental limit, we can say, no, we have a limit because we don't have enough frequency channels, say, to measure the foregrounds. The dust and the cyclotron in our galaxy, we have to peer through that. If we don't have enough channels, but just tell us, no, you have to go to space to get the frequency coverage. It could be something like that. So I'd say we will know in 10 years whether we absolutely need one to go to the next level. Certainly right now, you want to absolutely develop both of them. They're sort of complementary. Is that?
Well, maybe I can try different.
Thank you. Models of satellites put a factor of, in the tensor scale ratio, a factor of about 100 improvement of where we are now, both in space and on the ground. I should say, but also think, if you did this on the ground and you saw a signal, you would in that case, you'd absolutely want to go to space. Because the measurements you can make from space are so precise. It's because you can control the environment of your spacecraft so well. I'd say if there were a hint of it, you'd absolutely go to space, and otherwise it's a matter of timing. Perfect. You have a question in the back here?
Yeah, now that the Simons money has all of the teams cooperating as opposed to competing, is there something you can do with the multiple instruments that you're going to have on the sites that you could not have done with just a single one?
Yes. So what we're to run into is so far the teams have just been able to measure the population, which is great. And pretty soon, the signal we're after will start to be confused with what's called lensing B modes as opposed to primordial B modes. Like the primordial B modes are the ones that would come out of the Big Bang. The lensing B modes are just produced from those E-mode, B-mode stuff. But the lensing B modes are by gravitational lensing of the E-mode signal. Okay, so we're just about at the level where we have to clean that out. To clean that out, you want a high-resolution instrument. So the union is you use a high-resolution instrument in combination with a low-resolution instrument. The low-resolution instrument measures the core signal we're after. The high-resolution instrument cleans out the lensing. Okay. Another complementary way is these are hard measurements. I would never leave the result from one group. Right? And you shouldn't. These are hard. Work at the limits of noise. You need confirmation. You need someone else, and then even amongst groups we can divide it by frequencies, right? Because these are going to be measurements that were taking place over half a decade or a decade, and you don't want to, it's better to distribute the load. You don't want one group doing everything, so you split things up. So there are multiple ways to work together, and we're all buddies up there, right? We'll figure it out, and we'll rely on our competition to keep us honest, right? So let me perhaps ask one quick question. You were mentioning Fourier detectors with them here, right? We're talking about hundreds of thousands of them now. Can I get you just to reflect on this a little bit of how we get there in the next few years? Yeah, no, it's just this field, you saw that advance in the pushing down of the level of these fluctuations, and it's all driven by these technology development, and actually driven by people in the field trying to improve the detectors, because we can learn so much. And this is just one. This is just one of the things we can learn, right? Along the way, we should be able to determine the sum of neutrino masses. We'll put new limits on the number of relativistic species in the universe, right? There's just tons and tons of things you can do, so it's really exciting. And it's just driven this incredible technological development. And part of that is these detectors. The ones we use come out of NIST. There's a group at Stanford gearing up to build another one. Actually, the father of the detectors we use is Ken Irwin. He's here. There's another group at Argonne. There's a group at Goddard Space Flight Center doing them. There's a group at JPL, and there's a group at Berkeley, right? And it's going to take everyone to go from, now we have a few thousand, 3,000, and we want to up that factor of order 10, and that'll be on this time scale. Wonderful. All right, let's thank Lyman and all the speakers of this morning session.
So thank you very much for that, and of course, thanks for the opportunity to be here. I do want today, first I have to show I have my medical credentials here. The Truth in Advertising. I am a consultant for a company called Ionis Pharmaceuticals, who's been an intimate partner in part of the work I'm going to describe today. But the beginnings of the story that I'm going to tell is the recognition from human genetics that where we know genes that are either causative or contributory to disease, they're expressed broadly in many cells in the nervous system, not uniquely within individual kinds of neurons whose degeneration or dysfunction causes a specific disease. And even more so, work from an earlier Breakthrough Prize winner, John Hardy, he discovered that if you know how you inherit one copy of each gene from mom and one from dad, if you actually happen to inherit 3 copies instead of 2, perfectly normal gene, but 3 copies, and it's a specific gene encoding the product alpha-synuclein, you will get Parkinson's disease. And if you inherit 3 perfectly normal copies of a different gene, one encoding amyloid precursor protein, you will get early onset Alzheimer's disease. So gene dosage matters. And no mutations needed there. Gene dosage matters. And you could also then recognize that, well, you could be directly on the mechanism causing those diseases if you could just lower the synthesis of the disease-causing gene. And we set out to try to do that, but started an example of the disease amyotrophic lateral sclerosis, or ALS. The Americans call it familiarly Lou Gehrig's disease. And this is a disease where the neurons,